Hello, dear learners, and welcome back to the Lesson BCE YouTube channel. Today, we are diving right into the heart of nuclear physics. In this explainer, we're going to unpack the structure of the atomic nucleus, explore these crazy strong nuclear forces, and decode the mystery of mass defect and binding energy using, you guessed it, E equals mc squared. Let's jump right in.
Okay, think about this for a second. We know from basic physics that like charges repel each other, right? So, if the center of an atom is just packed with tightly bound positively charged protons, logically, that electric repulsion should just blow the whole thing apart. But it doesn't. Why not? Well, that is the central paradox we are solving today.
Here's our roadmap. We'll start by looking inside the atomic nucleus. Then we'll meet the strong nuclear force, unravel the missing mass mystery, dive into binding energy and equivalency, run some real calculations, and finally, look at medical applications in action.
All right, part one, inside the atomic nucleus.
It is honestly incredible just how packed everything is down there. At the absolute center of an atom lies the nucleus, and this contains your positively charged protons and your uncharged neutrons. Almost all the mass of an entire atom is concentrated right here in this super dense core.
And when I say it's a core, I mean it is impossibly small. Seriously, the atom is 99.99% empty space. To put that into perspective for you, the nucleus is roughly 100,000 times smaller than the atom itself. It's like if the atom were a massive football stadium, the nucleus would be a tiny little pea sitting right on the 50-yard line.
Moving on to part two, the strong nuclear force.
This brings us to the hero of our story, the strong nuclear force. This is the ultimate glue. It's that residual strong interaction that binds protons and neutrons together. It completely, and I mean completely, overpowers the electric force that's desperately trying to push all those positive protons away from one another.
Now, the crucial thing here is understanding its unique properties. It has a massively strong magnitude, but it only works over an incredibly short range. We're talking about roughly 1 femtometer. It's also charge independent, meaning it acts exactly the same whether it's between 2 protons, 2 neutrons, or a proton and a neutron. And here's the brilliant part. At distances below 1 femtometer, it actually becomes a repulsive core, preventing the particles from just collapsing and merging into each other entirely.
This really illustrates how the force operates down on the quantum level. This nuclear stability is the result of nucleons constantly exchanging virtual mesons, specifically pions, back and forth. Think of 2 ice skaters tossing a heavy medicine ball between them. The constant act of throwing and catching that ball keeps them locked in this specific, highly stable dynamic.
Which leads us perfectly into part 3, the missing mass mystery. Okay, get ready for a plot twist. If you take the mass of individual separated protons and neutrons and weigh them, they are remarkably heavier than when they're glued together into a combined nucleus. Just let that sink in for a second. When you put the atomic pieces together, the whole is literally less than the sum of its parts. So where on earth did that extra mass go? In physics, we call this missing mass the mass defect, which we represent as delta M. You calculate it by taking the sum of the individual proton and neutron masses and subtracting the actual mass of the formed nucleus. But obviously, mass can't just vanish into thin air, right? Let's figure out exactly where it went in part 4, binding energy and equivalency.
Here is our key equation for today, and you probably already know it. Einstein's famous mass-energy equivalence, E equals mc squared. This elegantly shows us that mass and energy are essentially just 2 sides of the exact same coin. The missing mass didn't disappear at all, it transformed.
That transformed mass actually became the binding energy. This is the energy you'd need to separate a nucleus back into its individual nucleons. So the missing mass, that mass defect, was converted entirely into the energy that now holds the nucleus firmly together. And a higher binding energy simply means you're looking at a much more stable nucleus.
When we plot the binding energy per nucleon across different mass numbers, a really clear peak emerges. Iron 56 and its neighbors sit right at this maximum point, making them the most stable nuclides in the entire universe. Elements heavier than this can undergo fission to release energy, while the lighter elements yield energy through fusion.
All right, part 5, calculating the energy.
Let's actually do a solved example together to see this in action. Let's say we have a tiny mass defect of just 0.002 kilograms. We use E equals mc squared,
So we take our 0.002 and multiply it by the speed of light squared. That's 3 times 10 to the 8th meters per second, all squared. Which means we're multiplying 0.002 by 9 times 10 to the 16th.
And the resulting answer is absolutely staggering. 1.8 times 10 to the 14th joules. That is a monumental amount of energy derived from literally just 2 grams of missing mass. It perfectly proves our main lesson today. A really small mass produces a huge amount of energy.
Let's look at how we use this in Part 6, Medical Applications in Action.
This isn't just theoretical math. The physical power of the nucleus drives our modern world in so many amazing ways. We see it in nuclear power plants providing atomic energy, all the way down to life-saving medical procedures. In medicine, nuclear physics gives us radiation therapy, like targeting tumors, and incredibly advanced radiodiagnostics for medical imaging.
For example, compare a traditional CT scan to an advanced PET scan. An XCT uses X-rays to give us really good morphological, structural images of the bones in the body. But positron emission tomography, or PET scans, use radiotracers, driven by the exact nuclear principles we just talked about, to give doctors these incredible functional images of the brain and body actively at work.
So, what is the core takeaway from this explainer? It all boils down to this. Small mass leads to huge energy. Because of mass-energy equivalence, microscopic changes in mass within the nucleus produce the monumental energy that powers stars, modern reactors, and life-saving medical scanners all over the globe.
Before we go, I want to leave you with a quick practice problem. Let's say a nucleus has a mass defect of exactly 0.001 kilograms. Go ahead and find its binding energy, and comment your answer down below. And while you do that math, think about this. If that much energy is hiding in just a single gram of missing mass, what else is hiding in the 99.99% empty space of the atoms all around us? That's all for today. Keep learning physics, and don't forget to subscribe and like our channel for more lessons. See you next time.